we now move to algorithms for linearizable registers. So we will just review the definition of linearizable registers quickly. So our termination is wait-free, which is if a node is correct, each read and write operation will eventually complete. And then we have linearization points. It's a linearizable execution we have. So informally, read operation appear as if immediately happened at all processes at the time between the invocation and response, and the write operations appear as if they immediately happened at all nodes between the time of invocation and responses. This guarantees that if one operation precedes the other in the execution or the trace, it will precede the other operation in the sequential trace. Then we have failed operations. With linearizable registers, failed operation appear as if it is completed at each process. You remember when we had partial execution or partial traces, we can complete them by adding responses, or as if they never occurred, and this by removing the invocations of the operations. So we have our linearization points, but initially we are going to work with algorithm for single writer, multiple reader. And in fact, in this case, we can extend our regular register definition of validity. If you remember validity from the regular registers, it says a read returns the last value written, if not concurrent with any other write or not concurrent with any failed operation. Otherwise, it will return the last value written or the concurrent write. We add an extra condition here, and this condition we call it ordering, and it says if a read returns the value R1 precedes a read that returns the value R2, then we impose a condition that the write that wrote the value R1 should precede the write that wrote the value R2. Remember, in single writer, multiple reader, all writes are ordered. Therefore, if a read R2 is after the read R1, then it is not possible to have the write of R2 before the write of R1. Once we have that definition, and this for single writer, multiple reader, it is easy to show that we can create linearization points. And of course, linearization point implies that this condition holds for single writer, multiple reader, where all writes are ordered. There is no overlapping writes. We will see this in examples. So let us look to this example. And in this example, we are violating atomicity because, as you can see here, we have this read here, which comes after this read, but it returns the value of the previous write. This is, of course, is a regular register implementation, and we have the read of 6 before the read of 5, as you can see, but it is not linearizable because in a linearization execution, the write 6 is before the read of 6, and we know that the write of 5 is before the write of 6. So this result here is not legal in a sequential execution, because in a sequential execution you return the last value written. So this is not legal. So which means that this execution is not possible to find linearization points for. Here is an execution which is completely fine. We have now this read returns the value 6, which is completely fine. We can have both this read and this read in the linearization point after the write of 6. So these give you a single system image or linearization points as follows, as you can see here. we do this write, and then this write, and then this read, and then this read. And that is completely fine. So in this example, we have also a linearizable execution before the requirement of linearizable execution that this read has to be after this write and before this read. And that is what the linearization point can achieve. So here we have this, and then we have the write, and then we have the final read here. So now let us look at an example. Here we have an example that is sequentially consistent. And remember our read that reads the value 5, which was not linearizable. In sequential execution, we can just place this read before this read, which is allowable in sequentially consistent executions. So we get the following. We get that write, followed by read 5, followed by write 6, and then followed by read 6.